Good morning. I'm Chris Salvino. Welcome guys to this really cool topic. We're going to be going over the coolant for quantum computers, helium-3, and what happens without it. And I want to thank our panelist and my co-host, Drew, as we jump into this exciting topic. Again, the discussion today is focused on helium-3 and what happens in quantum world with and without it. This series that we're discussing today covers everything that revolves around lunar helium-3. Each event examines a different implication of helium-3. For example, in December at our inaugural event, we discussed the value proposition of returning back to the moon. Is it going to be for a cost center, such as the Artemis program, or a revenue generator, such as resource like helium-3? And so together, our series asked the question whether helium-3 will enable a future moon to Earth-based economy. So many people on this event today, some people have a background in science, some people don't. Some people are experts in fusion or quantum, and some are just interested in space and green energy. So to level set, we have a few slides to get everybody on the same sheet of music. Helium-3 is an isotope of helium with very special use cases on Earth, which we'll talk about. On Earth, it's manufactured in some respects as decay of tritium from nuclear weapons, such as during the Cold War. It cannot be manufactured at scale on Earth, and our estimated supply, for example, in the United States is less than 5 kilos, and it's similar with minimal supply across the globe. It mainly comes from the sun. It travels with the solar wind, and on Earth, it's captured by our atmosphere. So there's very little on the ground on Earth due to that effect. On the moon, it's been baked because there's no atmosphere into the ground for billions of years. The difficult part about it is the concentration of the moon is about 1 to 15 parts per billion, somewhere in that range. So stay tuned to some of our future series to discuss how to extract helium-3 using a lunar technique and not an Earth-based mining technique. Now, the good news is there's a wild estimate of 1 million tons of helium-3 on the surface of the moon. That could be 100,000 tons. It could be 2 million tons. There's a lot of it on the moon to power fusion and other issues for the future. So helium-3 has some demand. There are existing use cases such as cryogenics, and most important, most likely, is neutron bomb detection or nuclear bomb detection for border security. The problem is we're running out of helium-3, so there are workaround solutions being used now for these existing use cases. In the future, we'll be looking at much larger volumes of helium-3 needed for nuclear fusion and quantum computing. The interesting thing about nuclear fusion, which we explored last month, there are two optional fuel sources. The one that people are using now is tritium, and the alternative, if they can get it, would be helium-3. The take-home message here, which is really important, the only scalable green energy source across the globe would be fusion with helium-3. So go back if you want and look at our videotapes on our website about that topic. We'll be rediscussing that in the future. And then quantum computing today, we'll be discussing how important it is to be used as a coolant for high-speed computation and its importance in national security. So those are the use cases, but the use cases to go to the moon would not matter if the price of helium-3 was like $1. So the current price of helium-3 is about $30,000 a gram. That's actually less than tritium for nuclear fusion. That price may go up or down, but that's in today's dollars. That's $30 billion per ton. If you look at the future use cases, if fusion goes across the globe and is being fueled by helium-3, the total addressable market is about 570 metric tons per year in the future. That's $17 trillion worth of revenue. That's enough revenue to overcome the cost of going to the moon and back. On the quantum side, you need markedly less helium-3. We had made a back-end estimate of how many quantum computers there might be in 15 years, how much helium-3 they would need, and that comes out to about 4 metric tons. And that's a wilder guess, but it's still in the billions of dollars worth of revenue for quantum. We are starting here because for more than 60 years, the moon has been a cost center. Many people may or may not know there's been approximately 8 countries that have sent landers or orbiters to the moon, and that's all been governmental funding by those different countries and their partners. Helium-3, we believe, is the only resource that is tied to extraction on the moon. There's no other resource on the moon. There's titanium, gold, copper, all sorts of other resources, but it's too expensive to go there to extract them to bring back to Earth. Our company is hosting these series, and our only focus is on helium-3. Our questions have spanned space, energy, the economics of this. And this series is our attempt to bring those questions more publicly as opposed to internally. So this series is entitled From the Moon to the Earth, the Trillion-Dollar Helium-3 Frontier. This month's topic again is quantum computing. The assumption for today is that us or other companies have brought back helium-3 to Earth, so we will not be discussing the extraction process or the legalities of that. That's for future discussions, so please attend those. So the focus today is going to be on helium-3 and what happens with and without it, and should we care when it comes to quantum computing. And with that, we're going to bring our panelists in. I'm going to stop sharing my screen. And I'm going to turn it over to Drew to ask the first sets of questions here. So give it a second to load, and then Drew, you're up.
All right, I think I am good to go. All right, well, thanks everyone for joining us today. I apologize in advance for the lighting on my camera. I am in Hawaii at the moment. It's a little dark over here. I'm here in part to look at various lunar analog sites for mining. There's various places that people do testing terrestrially. Mojave Desert is one, and Hawaii has been a big one historically. So I'm here to kind of check out some of the different areas for some of the future stuff that we want to do at lunar helium-3 mining. But today we're here to talk about quantum computing. So first, I want to ask about, why do we even care about quantum computing before getting into the cooling aspect of it and helium-3? And so we all know that artificial intelligence dominates today's technology conversations. And so really the question is, has quantum computing become a buzzword of the past, or is it still a transformative platform that's strategically important where artificial intelligence maybe is not, in ways it can complement or maybe overcome? But where does quantum computing fit in this larger ecosystem? And this is really for either panelist that wants to jump in here.
I'm happy to do that. Yeah, so I mean, quantum computing is a very challenging problem that is gaining in momentum after many years of work, and continues to be I think, important technological topic. The real applications for quantum computing at the moment, as you know, we see things are certainly in the security area. Something called Shor's algorithm, which is in a lot of ways a killer app for quantum computing, allows for public key cryptography to be broken. That obviously has broad implications for security in various ways. But I think probably the more longer term impact of quantum computing really is in the simulation of chemicals and material systems, finding new types of materials, pharmaceuticals that are important for treating diseases, and building infrastructure from material systems and chemicals, such as catalysts that at the moment, for instance, fertilizer is an example at the moment, that is very energy intensive, very expensive to produce, but could be done far cheaper and with far less energy if we had an appropriate catalyst. And quantum computers are believed to be machines that are well suited to finding these types of chemicals that are needed for so many different reactions. So for me personally, though, I think the applications of quantum computing is probably something that we haven't really understood yet. And I think, you can look back at the history of conventional computers and ask to what extent did humankind anticipate the uses of computers that we have today back in those early times. So quantum computing is, I don't know, somewhere around 1947 to 1957, somewhere between the first demonstrations of the transistor but it's early days in terms of building out integrated circuits. And I think back then it was difficult to anticipate the many use cases that we have today for conventional computers. And I think it'll be very similar with quantum.
Yeah, we've kind of seen how artificial intelligence is changing the world. I've never seen a movie where quantum computers are, really prevalent in kind of what they're doing. So it's not in mainstream media. I don't think people are talking about it anymore. So what is it about quantum computers that changes people's maybe people's everyday's life? Is it going to cure cancer? Is there anything else that just the normal person can see out of what quantum computing can really bring?
Yeah, I'm happy to keep going on that. So I think, the intersection between artificial intelligence and quantum is one that's evolving and one that we're really still, I think, exploring at this point in time. There are definite use cases where what you might call, the kind of conventional AI approaches that we're seeing disrupt so many areas of industry will also have impact in quantum computing research. But I think the most exciting opportunities are really in some ways to ask the question, how would I train an AI model to develop an intuition of quantum mechanics? And quantum mechanics is the underlying physics of reality. It is the physics that governs, everything from our technologies through to many natural phenomena. And so if I wanted to build an AI model that had been trained with data that really captured the phenomena of quantum mechanics. How would I do that? And so one potential opportunity for how that might work is that a quantum computer, in fact, could be used to generate quantum data and large amounts of that. That's then used to train, a more kind of conventional AI model, but a model now that's been developed from that unique quantum phenomena and data that emerges from a quantum computer.
Well, that's interesting. I know for artificial intelligence to work well, you have to have a lot of data. So that's something I hadn't even considered before, where quantum computing can create just tons and tons and tons of data that AI could use to train models. I like that. That's interesting. So in simple terms, what is a quantum computer? How does it work? How does it operate? How does it get us to places where conventional computers cannot?
So, yeah, to maybe develop some intuition about a quantum computer, this is obviously a very challenging topic and a vast topic in its own right, but essentially a quantum computer derives its power from the interference of what you might call quantum mechanical wave effects. And this is already becoming, kind of mind-bending in some ways, but maybe if I say it in terms of, if you go back 100 years or a little over 100 years, it was Einstein that realized that light had this sort of dual personality. It behaved like a particle, like a photon, what we'd now call a photon. But of course, light also behaves as a wave and exhibits phenomena like diffraction and interference. And light is both particle and wave. It was in 1927 that de Broglie recognized that matter, atoms, electrons, neutrons, also have this sort of dual characteristic that they behave like particles, of course, in a way that we're used to them. But matter also has a wave-like character, and this is the basis of a lot of modern technology. A quantum computer is actually using that wave-like character of matter or light to do interference. And when you're kind of building a quantum algorithm, the name of the game is to effectively create a scenario where the answer that you're looking for from your quantum algorithm emerges from the constructive interference of many of the inputs, and all of the wrong answers effectively cancel one another out from the destructive interference of the wave-like aspect of quantum mechanics. So it's an interference machine. If what I just said sounds a little familiar to people that are maybe historically familiar with analog computing, then that's absolutely right. This is very similar to sort of the analog computing of the 1970s, 1960s, and so on. But instead of interference of electrical currents or voltages and the wave-like character of those systems, it's the interference the wave-like aspect of quantum particles itself, to be able to do effectively analog computing with that quantum mechanical wavelength. So that's a lot of physics. There are a lot of counterintuitive aspects to quantum mechanics, quantum measurement, quantum entanglement, and so on. And these are also important resources and phenomena that are exploited in the construction of a quantum computer.
Excellent. And then maybe Dr. Kumar, how big are quantum computers? Like we have laptops on one end that everybody's using now for this meeting. On the other end, we have these very large data centers that are being built to support large language models and really AI and where it's going. Where does quantum computers sit? Are people going to have one in their living room? Are they really just lab scale? Kind of give us a scale of how big these things are.
Well, so you see, when normal or classical computer, when they are developed long back, so you should look at the first classical computer which was made using the vacuum tubes. And at that time, those classical computers were too big, and having just 100 byte of memory, they were occupying a big room, weighing around 20-30 tons. The turning point in the classical computing came when the transistor came into picture, a semiconductor came into picture. And after that, the classical computing or semiconductor industry never looked back. And you can see that the size of the transistor start reducing every year, twice. And now we are at the stage where the further shrinking the chip is getting difficult, because in the MOSFET, you can see when you talk about drain to source, that is the distance matters in the chip. And the gate which controls the flow of electron from the source to drain. And already we are somewhere at 3 nanometers, the separation between the source and the drain. And if you try to further go down, okay, then you can see that the quantum tunneling from the source to drain will start taking place. And at this stage, the role of the gate is no longer going to play anything. So it demands that we are at the stage where the further reduction in the size is going to be difficult in couple of years or maybe in the decades, and where we are now looking forward toward the quantum computing. So at the moment, size of these quantum computers are as big as the early days classical computers. So when you talk about tube-based classical computers having memory just 100 bytes, weighing around 220 tons, similar kind of situations we are facing at the moment in the quantum computing. So although the size of the quantum chips are very small, but the surrounding, particularly the dilution refrigerator, which actually used to cool down the whole system to maintain the coherency of the quantum states, those equipments are very bulky. And because of these bulky equipment, these quantum computers are getting big. So at the moment, they are very big, definitely. But what I would like to also add that maybe we are still in the quantum computing, we are still in the era of vacuum tube of classical computer. And maybe in few decades, we may find a new breakthrough, the way we found a breakthrough in the classical computing with the invention of semiconductor technology. A similar kind of breakthrough may happen in the quantum computing also, where the cooling particularly may not be required. And if the cooling is no longer required, then the size of the quantum computers will be going to be very small. As small means smaller than the laptop size as well. But it depends whether we are able to crack that code of the nature where the quantum interference and the quantum coherence may even sustain at room temperature.
Yeah, that's interesting. People have been worried about Moore's law for a long time, but I think we are coming up to the edges of what Moore's law can give us for classical computers. So it sounds like, from a timing perspective, when we start hitting the edge of Moore's law, maybe quantum computers will start kind of coming up and being able to replace and overcome that. So from a consumer perspective, really, you can't tell a difference. Computers keep kind of scaling because of this kind of transition over from classical to quantum computing.
Yeah, but I mentioned that I still feel that we are not still able to crack the rule of the law of the nature. For example, if you look at the bigger issue is to maintain the coherent state in the quantum computing. And if we can maintain this coherent state, so we are fine. For example, if you look at the in the nature, there is a phenomena which is called the photosynthesis, and it is the still we are not able to understand how this photosynthesis is taking place. And in the photosynthesis, uh, where this coherence phenomena is taking place at a room temperature. So if you look at the sunlight is falling on the leaf, and inside the leaf, the sunlight is interacting with the chlorophyll, and on the chlorophyll you can see it create excitons, and these excitons then they are hopping and reaching to the one energy center point, and you can imagine that in huge number of excitons are reaching to the one point, and it seems like they are creating some kind of conspiracy, so they are in the coherent state. And these coherence, how they are taking place in this photosynthesis process is still we as a scientist unable to understand. And the day if we manage to understand this very basic nature's phenomena, I think we will be able to create a quantum computer even at a room temperature, and that is going to be much smaller, 1,000 times smaller than what we are seeing in the world. For example, IBM or any other industries who are showing up their quantum computers. So we are still
Yeah, so
waiting for this transition from the vacuum to semiconductor, a similar transition in the quantum computing also.
yeah, Dr. Riley, do you agree? Is there going to be a quantum Manhattan Project event where there's a singular event that kind of jumps us over the edge, or is it going to be more incremental?
Yeah, so I probably have a contrasting point of view on a few of those topics. Just to go back a little bit there, I don't think that conventional, classical computing will ever go away, and there will be a transition to quantum. In fact, quantum computing's often misunderstood as being some sort of all-powerful computer that will do all of your computational workloads in some, as if it were some sort of modern extrapolation of the way we use computers today. But the use cases for quantum, as I said, at the moment are actually pretty narrow, and I think we will continue to have conventional classical computers working in tandem in some heterogeneous compute platform, as you have GPUs today, CPUs, TPUs, where we see analog accelerators, neuromorphic systems. We're adding a quantum, I think, to that mix, where certain workloads that are well suited to quantum problems, like materials and chemistry, as we were just talking about, will be part of that workload will be handled by quantum. But quantum computers today and in the future actually will need high speed, powerful, high performance computing of the kind of classical kind for their operation, for their control, for error correction, and so on. And so, yeah, it's really a combined system. Um, my personal opinion in terms of the possibility of room temperature or even higher temperature operation. There are certain regimes for sure where that is possible, and in fact, one of the leading platforms in quantum computing at the moment, neutral atoms, is largely at room temperature, but it is the exception. All of the other mainstream physical platforms that people are pursuing for quantum computing, whether it's superconducting qubits, that you see at IBM, at Google, at AWS, spin qubits that you see at companies like Intel and many startups, particularly here in Australia, trapped ions and photons, all are leveraging extensive cryogenic apparatus. And that I think is in some ways a technological driver or a technological limitation of where we are today. But I think also when you really unpack the underlying physics there, it's hard for me to imagine, with as I said, some exceptions, but for the mainstream approaches, that those will ever really have utility at higher temperatures. And in fact, obviously, if it was possible to build a machine at room temperature or higher temperatures, that's a worthy goal. Many people are working on that. And there are examples of prototype machines that are operating at higher temperatures, but there is a trade here. So operating is one thing. I think the key question is, what is the fidelity of your qubits, which is the building block of your quantum computer. What is the fidelity of your gate operations? What is the fidelity of your readout, your preparation? And I think when you start to put metrics like that, all of those metrics are degraded as a function of temperature. So, a demonstration and operation is one thing, or the possibility of, as we were just discussing, there are examples where you can see aspects of quantum mechanics, aspects of quantum coherence at room temperature. But I think that's a far step from saying that you have sufficient fidelity to really control and scale a quantum computer. For me, that's still very much the domain of low temperature physics.
Yeah, so there's more than one way to make a quantum computer, as you were alluding to. So what are the different kinds of quantum computers, and why is cryogenics so important to reaching what we need to do?
Yeah, it's interesting that the field started a couple of decades ago, and started with these very different physical platforms. And like classical conventional computing, we're kind of been born and raised in the decades of transistors, and we think that computers are built from transistors and silicon, and but of course you can build a machine that computes many different ways, from an abacus through to mechanical machines and so on. And similarly with quantum mechanics, there are various ways to leverage the underlying physics of quantum mechanics to be able to compute something. So if you go back to sort of 25 years ago, there were a variety of physical systems that people were leveraging and exploring as ways of tapping into quantum mechanics, and certainly single photons was one approach. Single electron and single nuclear spins has been something that is very interesting because it's in the solid state in condensed matter. Superconducting qubits, which leverage both obviously the lack of dissipation in superconducting materials, but also properties of superconducting junctions. And then trapped atomic ions, which traditionally have been very much a room temperature physical platform. But it's really interesting to me, having been in the field for 30 years, the convergence now of all of these platforms are all operating at least liquid helium temperatures. And at least two of them, at temperatures below liquid helium 4. And superconducting qubits, spin qubits, in the present era, certainly leveraging helium-3 diluted with helium-4 to get down to temperatures of order 100 millikelvin or below. And I think trapped atomic ions, certainly chip traps, operating now at 4 Kelvin liquid helium temperatures, as are photonic systems. So the convergence is pretty interesting. It's maybe a good question to ask, is 4 Kelvin helium-4 a low enough temperature? What are the advantages to going lower, even for those systems that at the moment are still at those slightly elevated temperatures?
Yeah, I do want to transition over to Helium-3 and hand it over to Chris to continue on. But I have one more question, and maybe Dr. Kumar, if you could comment on this, because you talked about higher temperatures. So I know of late there's high temperature superconductors, which are liquid nitrogen type temperatures. And me being ignorant in quantum computers, is that telling us that maybe since we're doing superconducting qubits, we could potentially go up to higher temperatures, maybe helium, maybe nitrogen, things like that, or are we really limited to those very, very low temperatures?
No, I mean, not only think about superconducting qubits, but there are other platforms. So, for example, we can also think about photonics quantum computing, which can actually work at a room temperature. So, if in the future, if you can manage to create and maintain the entanglement and qubit, and if we can find a proper way to read out mechanism for the photonic qubits, then it is another very good source now to look at the room temperature quantum computers. So regarding the superconducting, uh, at the moment, we have to stick to the low temperature. I agree with David as well. So majority of the technology which are emerging at the moment, particularly in the superconducting qubits, we it's very challenging to move toward the high temperature superconducting materials. So we have to stick to the low temperature at the moment. But instead of sticking only to the superconducting materials, better to explore the other domains. As I mentioned earlier, also that uh, none of these platforms are still uh, proven to be the 100% only viable method to go for the quantum computing. So we are still exploring the all possible ways. So like superconducting is the one which is very easy to actually create the qubits. Scaling is very easy in the case of superconducting. But other platforms, for example, think about the ions trapped in the Paul trap, another possibility. Think about the electron spin also in the semiconductors. In fact, myself, we are working on the electron qubits, but not in the Paul trap, but in the panning trap. So we are exploring this possibility to create electron spin qubit, but we also working at a low temperature. So what I'm trying to say that instead of digging out only in one material, that is the superconductors, it is better that we should explore the other possibilities. Technically, to make a quantum computer, you need two quantum states. And if you can make these two quantum states in a superposition, this can act as a qubit. You can create a qubit. So this is not the only possibility. Superconductor is not only possibility. There are many other possibility which exist. So I think this is the time at this moment when we are exploring the possibility. This is time to explore the all possible situations, all possible materials, which can maybe, as I mentioned, that maybe in the future we may find a suitable platform which actually resembling with the nature. In the nature, superposition doesn't need to go for a low temperature. In the nature,
Great. So what I'm here
superposition taking place at room temperature.
Great. So what I'm hearing is in the near term and even into the far term for sure, we need to get to these very, very, very cold temperatures, and there might be a breakthrough in the future that allows us to get away from that. But in the interim and in the meantime, and maybe even into decades, we want to get to these very low temperatures.
I
All right,
agree.
Chris, I'm going to turn it over to you to chat through helium-3 and the requirements there to reaching those low temperatures.
Okay, cool. Thanks, Drew. And for Dr. Kumar Riley, maybe we could do a little rapid fire thing. We can go back and forth between the two of you. These are kind of quick little questions. Let's level set again. Dr. Riley, what temperature does the ideal quantum computer operate at approximately?
Yeah, it's a great question. Obviously, there are various trade-offs there, and abundance of helium-3 or lack thereof is obviously a key one there. Look, my personal perspective is that I think when you zoom out from the physics of a qubit to a system and include things like detecting single photons or being able to do the readout of quantum states with very high fidelity, then you will always want to be at the lowest possible temperatures from the point of view of the physics. And I'm actually pretty skeptical that you could build a machine at scale when you really evaluate the noise sources, which of course thermal noise, but many other effects that lead to a degradation in the performance of a scaled quantum computer. have a temperature dependence. So if you look at, I think, trapped charges on surfaces, thermal activation of noise sources of various kinds, and so on, background pressure of vacuum chambers. There's much more to it than the underlying energy levels of the qubit itself. It's also the performance, again, at scale of what these machines have to do in terms of the readout, in terms of the control. I think it is a crossover, and a kind of a sweet spot where the lower you go in temperature, the better your readout, the better your control, the better you can really control many of these noise sources. However, you're often, you're losing cooling power as you're going to lower temperature, irrespective of what that cooling technology is. And so as you're going lower and lower, then your ability to extract heat is diminished. Then, of course, there's the technological questions around how much helium-3 there is, how expensive these machines are. I was interested in your opening remarks, Chris, around sort of how many quantum computers are there in the world. And I think, that again, that's something that I think nobody has really good handle on predicting. But just to maybe consider what I had said in the opening discussion, that quantum computers won't replace conventional classical computers. At the same time, these quantum algorithms that we're so excited about, they're kind of probabilistic or stochastic. You need to run that algorithm many times. So a single quantum computer that has to run for 6 months and then run again for another 6 months and run again for another 6 months is not so useful. And I think the model that people have in mind at the moment are, very large data centers with farms of quantum computers, mapping out the parameter space of a particular problem. So yeah, I think that you end up with a very large number of quantum computing systems, a very large number of dilution refrigerators, and an enormous amount of helium-3 and helium-4 to really get at those very challenging problems at scale. So what's the ideal temperature? As low as you can go, where you still have an economic model and driver and business case for being able to build these machines at the lowest possible temperatures, and with consideration to the diminishing cooling power as you go to lower temperatures.
So would 0.01 Kelvin be a theoretical low temperature goal to shoot for?
There's at the moment, I think, a lot of effort and excitement in operation around 1 Kelvin. And 1 Kelvin is a temperature achievable with helium-4 under pumping conditions, lowering that vapor pressure. Again, though, I think it's early days in those approaches. I would be cautious to distinguish the basic demonstration operation. It works. Look, there's a qubit, from how does the fidelity of that qubit and the control and the readout scale with temperature? What did you give up by going to that slightly elevated temperature? So there's approaches at the moment where the qubit may be at 1 Kelvin or even 2 Kelvin or so on, but the readout and amplifiers and the control system are in fact still at 100 millikelvin. And I think we're going to see those types of temperature gradients and sort of hybrid cooling approaches as well, where there are physical parameters that you really want at the lowest possible temperatures. There may be other parts of the system that are dissipating more power, and you can live with those being at slightly elevated temperatures. And I think we merge to a cryogenic solution that has independent cooling pathways, both dilution systems as well as more conventional pumped helium-4 working together.
Dr. Kumar, is there any solution besides helium-3, helium-4 that can get us down to those kind of temperatures? We've talked about a lot of different things going on. Some of these questions may be repetitive, but those, when we look into this from a layman's point of view, appears to be the most practical, maybe the only way to get down to these temperatures. Is that a true statement, do you think?
Yeah, I mean, so if you want to cool down, so this one way is to physically cool down the system using the helium or helium-3, helium-4. But in some system, for example, in the ion trap qubits, uh, we don't need their helium-3, and there the cooling can be done with a laser also. So we can do a laser cooling, and we can go to as below as microkelvin temperature. So if you ask, I mean, there are different way to cool down the system, but if there is a heat load is very high, then definitely you have to stick to the uh, cooling, physical cooling through helium-3 or helium-4.
Here's a tricky question, Dr. Riley. Are companies building quantum computing systems under the assumption they will have helium-3 as a coolant source?
Yeah, I think so. And it's a little bit like I think what we're seeing at the moment in AI. There's a race on, and what you're seeing, I think, in the construction of data centers for training, language models at the moment, a brute force, white knuckle approach. I think if you look at what the scale of data center that XAI has recently completed and so on, these are just astonishingly large systems requiring enormous amounts of energy, cooling water, and so on. And the reason for that brute force approach is, whoever can build that large data center and run that many GPUs can train the biggest models, thereby kind of win the race. And then, having won the race, I think strategically you would assume that that's going to lead to a rethink in the underlying infrastructure. And I think similarly in quantum, what we're seeing is a brute force approach of just like get as many dilution refrigerators as you can, control as much as you can using, conventional means. And then, whoever sort of dominates and wins that, maybe is in a position to start more of a R&D program to develop more efficient approaches. There are, of course, alternative directions in many companies, like Emergence Quantum, that are really trying to look at more scalable approaches from the beginning, and believe that this sort of brute force approach will be pretty challenging, even to get to systems of moderate scale. But I think you're seeing both at the moment, and yeah, in that brute force approach, yeah, I think the assumption is there is or will be a abundance of helium-3 needed to power those very large farms of dilution refrigerators.
And Dr. Kumar, if they're making the assumption they're going to have helium-3 and across the globe the supply is almost gone, I see there's a major disconnect potentially there. Are they promising something that's just not going to be there? Do they know something we don't know? Because the supply from the breakdown of Cold War nuclear weapons, the supply, for example, in the US, we assume is under 5 kilos and it's dropping. So what's going on there? Are they lying, or is it going to happen? We just don't know how. Are they going to? So where do you see? There's something that doesn't make a lot of sense. People are building stuff. Are they assuming that they build it, it will come?
I means I cannot comment on this part, what's going on inside. It is a very political question. But uh, on a technology point of view, I can definitely say that yes, if we are not getting enough helium-3, then this is going to create a problem in the further scaling a quantum computing system across the world. So majority of the quantum computing at the moment relying on the superconducting qubits where this cooling is required definitely. And if any case, if because of the political or geopolitical situations, if we are not able to get this helium-3, we will be in trouble.
Okay, and that's a good summary. Thank you. Let's now look into numbers. So jump with Dr. Riley, but if you guys want to go back and forth, let's talk about volume and numbers. So what I've been reading about this is the average quantum computer, we're now using helium-3, may need 8 to 40 liters of liquid helium-3. Does that seem like a realistic amount in the lifetime of a quantum computer? somewhere in
Yeah, I
that
think
range.
so. I would say 30 liters at 1 atmosphere is a pretty typical number for, a standard dilution fridge.
Okay, let's
20,
move.
30.
And then, as long as you got that question, from my understanding, there won't be really any loss. It's not like it's used up, but there could be leakage. So if the quantum computer uses 30 liters in its lifetime, there may be a tiny bit that is lost due to some sort of leakage, but it's not obviously consuming it.
Yeah, correct. However, it's funny. I think amongst physicists who have long had careers involving helium-3, some bragging rights is that you've never lost, a milliliter, a gram. And there are, of course, though many horror stories of leaks. There's not a great deal really that stands between that helium-3 and the outside atmosphere. And yeah, most labs that have been operating for a sufficient amount of time with enough grad students, for instance, have some sort of experience with the loss of helium-3, unfortunately.
Okay, so if Dr. Kumar, would you agree roughly 30 liters per quantum computer, give or take? It's not like a million and it's not like zero. Just that's
It's again depends upon how many qubits you are actually looking for. So if you look at the small dilution refrigerator or medium regular dilution refrigerator or large scale or larger dilution refrigerator, so it varies. So David, what he said is very good numbers. So general dilution refrigerator requires around 25 to 30 liters helium-3, and the volume which provides this kind of a dilution refrigerators. So in this volume, then it depends how many qubits you can fit. So for example, at the moment, people are claiming to go for 10,000 qubits or 20,000 qubits, but these are logical qubits. And if you want to actually create millions of qubits, then it may be you need to either make a bigger size of dilution refrigerator, which then further going to extract more heat out of the from the heat load, and then this 30 liter will not work. Then you may then this dilution refrigerator will need now more amount of helium-3. So let us say if one dilution refrigerator able to or capable to hold, let us say, uh, 1 million qubits, or if you want to create, let us say, 100 million qubit, then you need equal amount of dilution refrigerator. So one lab will not going to stick with only one dilution refrigerator. So either the company like Blue Force, they have to come out with the bigger volume, or one has to purchase multiple dilution refrigerators, and each, let us say, carrying 30 liters, and one lab having, let us say, 5, 10 such dilution refrigerator, then these numbers are going to increase exponentially, I can say, in the coming decades.
so that those are all great answers. And I think we have a range, but I think the range we can kind of quantify is somewhere for normal purposes, somewhere between maybe 10 and 40 liters. Let's just say that's maybe the range. We have about 4 minutes to go, but let's break it down into let's change scales. If I've done the math correctly, I think you need about 59 grams of helium-3 per liter. Does that sound about right? So we're trying to figure out if you had 10 to 40 liters of liquid helium-3 for a quantum computer. If the math is right, it's somewhere between a half kilo and 2.5 kilos of helium-3 for that quantum computer. Does that seem about right to you guys?
What was your last conversion there? I didn't follow the last bit you said.
I think it's about 59 grams per liter. And if you're
Yeah,
looking
that
at
makes sense.
10 to 40 liters per quantum computer,
Yeah,
Yeah,
that's correct. Yeah.
yeah.
so So you need, I'm trying to get a handle on, because we usually talk about helium-3 in grams or kilos.
Yeah.
So it's probably safe to say looking at maybe a half to 2.5 kilos of helium-3.
Reasonable.
Yeah.
So it brings it back into an interesting discussion because, again, across the globe, that supply is down. In the US, we estimate it's potentially somewhere in the neighborhood of 5 kilos. And if these numbers are correct, there's not much helium-3 left to cool down these computers as we sort of look to wrap up here.
Yeah, that seems I have to do the numbers there. And when you say 5 kilos is all that's left, that seems surprising to me, given the volume of production at the moment of dilution refrigerators and the cost of buying helium-3 from DOE. If that were 5 kilos, yeah. So you're kind of saying that there's 10 dilution fridges left.
And there's some being, some by decay being produced. So I think the message there is we're quibbling now about the final details, but we're running out of it on Earth. It's really the supply's fairly low at the bottom line, and the quantum computers need a fair amount of it.
Yeah, I mean, I think across the various dilution refrigerator companies, not including other applications, but just on the fridges, the kind of numbers of fridges that have been sold per year now, is I think somewhere between 50 and 100 fridges. So yeah, and that's probably excluding some fairly large other orders. Yeah, so somehow that number doesn't marry up with that limited supply. Yeah, I wonder what we're missing.
Well, as we wrap up here, I'll bring one question back, and then we'll open it up to the audience, or if you guys have any other points. But I guess the ultimate question is why we had this discussion today is if we brought back helium-3 from the surface of the moon, would quantum computers use it? I'll leave that up to both of you guys to answer that. Would you want it if we can bring it back? And it's not just us, there's other entities looking at going to the surface to extract helium-3. Someone's going to bring it back. Do you want it?
So, I mean, my comment on that would be, obviously anything that can enable the supply of helium-3 to continue benefits not just quantum computing, but broadly the low temperature physics community, for which there are a range of other applications and phenomena that leverage helium-3. So the continued supply is one thing. Maybe another interesting question to ask, though, is in a world where helium-3 was abundant, what type of cooling paradigms open up? So now it's a question I think as to whether you could imagine mining the moon at such volume, but assuming that there's a pathway there, then I think it's the other part of the story is not just how we use helium-3 for cooling quantum computers today, but how might we use helium-3 for cooling scaled up machines if it were really abundant. And yeah, I can definitely imagine very different use cases there.
Dr. Kumar, thoughts? If we had a fairly good supply of helium-3, would you use it?
Why not?
Good, good answer. Okay. With that, let's go to the audience, and you guys can wrap up. There's two questions from the audience, or this one, and Drew, you can answer this one too. This one may or may not have to do with helium-3, but the first one's an interesting question because it's coming up in the lay literature. Do you see a move of large-scale data centers in orbit? Anybody want to take that one on?
Yeah, I'm happy to comment on that. I mean, I think the potential there, that the driver, is obvious. That yeah, I mean, paired with the right kind of communication and transceiver systems, than having data centers in orbit. Obviously has certain benefits. The real challenge there is the cooling. And if we're talking about data centers with large GPUs of the kind we're filling data centers with today, then that's pretty significant power when you think about, the cutting edge GPUs are dissipating nearly, several hundred watts, if not getting close to a kilowatt now, per GPU. And so you have to get rid of that heat. That's difficult to do if you don't have convection. That is, there's a working fluid that I can use to exchange that heat, or conduction. But if we're really talking about something in orbit, then radiation is the only means of removing that heat, and that requires an enormous amount of surface area in order to be able to efficiently extract that kind of heat. So I think, the technologies considered for those types of approaches are very large sail kind of architectures and structures that are trailing behind, some satellite in orbit, or vapors that are effectively, sprayed out into space. A lot of, I think, the fundamental technology for radiative cooling at scale there at the moment doesn't really exist. But sure, look, if there were developments there, then that becomes pretty interesting. But again, pretty challenging to remove, megawatts of heat via radiative cooling alone.
And thank you. We're almost out of time. That we're going to bring up data centers in one of our series in the future, talk about how you're going to power them. That's a completely different animal. There's another question, Dr. Kumar, if you could see it in the chat box, I put it in there for you. I'll read it because it's kind of complicated. We might have time to answer it in 30 seconds. Can you see it in the chat box, or I'll read it out loud? It's from Benjamin. The last one was from Steve. Thanks, Steve. And Steve, stay tuned for our data center discussions in the summer.
Can you read out, please?
Sure. When looking at the roadmaps for Millikan quantum cooling versus qubit manufacturing, do you think there's enough attention given to advancing qubit fabrication?
Okay. I mean, yeah, this I can say it is a very strategic, important question. When you talk about solving cooling, then when you look at the actual meaning, okay, so most of the solid state qubits, when you look at, so the base temperature goes to around 5 millikelvin to 20 millikelvin. That is given by our dilution refrigerator easily. Electron temperature also goes around 20 to 100 millikelvin. Okay, and so if you look at the state of the fabrication by any platform, so in the case of superconducting, so IBM or Google, okay, so they are, I mean, their strength involves the mature thin film processing, wafer fabrication part, okay, but they also have a bottleneck. So the bottleneck, like they are stick to the two-level systems now, or material loss, which is because of the microwave interference with the material. They have junction variabilities. These are the bottlenecks which are already exist. When you look at the spin qubit, are similar like Intel or QTechs. So they are also going to have their own strength. They're going to have their own bottleneck. So similarly, trapped ions. I mean, it's IonQ or my institutes where we are working on the trapping electrons in the panning trap. We also have our strength. We also have bottleneck. So for example, in the normal IonQ quantum computing, the bottleneck is the laser stability. And also the scaling is not so easy as compared to the superconducting one. Similarly, when you look at the semiconductor spin qubit, so this is also very interesting, but they also need a refrigerator which can reach to 10 millikelvins. They also have their own advantages and disadvantages. So if I talk that key whether the fabrication roadmap going to log this cooling, okay, then my strict answer will be no. Okay. So fabrication is currently the dominant bottleneck, okay, in the most platforms talk about superconducting, talk about ion queues, talk about semiconductors. Okay, in all this technology, the bottleneck is not the cooling. The bottleneck is actually is the platforms or fabrication platforms. So
Okay. And that's a great end to the series. Let me put up one or two slides. I want to thank you guys for helping us with this discussion today. It's been phenomenally interesting as we look at why go back to the moon anyways at all. We believe the main reason to go back is to extract helium-3 for multiple use cases. I want to point out over the next couple months or year, we plan on discussing different topics. The next one coming up is going to be really pretty cool. Who owns the moon? The legal reality of mining the moon. If, for example, one company goes there and another company from another country goes and sets a lander down in the exact same spot, what's the legal implications? If I go there and we extract helium-3, do we own the helium-3? So there's a bunch of legal questions we're going to be discussing next month. After that, we'll be looking at the economics in April of extracting helium-3. In May, it's going to be a fun one. The topic is space race to the moon. First off, the space race was completed in 1969, but space race rebooted. Are we going back there to plant a flag? Are we going there for a resource? China has said they're going to the moon to extract helium-3. India has said that. The US is going to the South Pole to look for research in water. So the May one will be very interesting. Why are we going back again? Is there a space race for a flag, or is it a space race for a resource? And with that, I'd like to thank everybody again for participating. And we did have, this will be out on the internet, I think on YouTube and on LinkedIn in the next couple of days. So again, thank you for your time today and your participation.
I think there's one more question, Krish, that what do you think about Large Hadron Collider cooling system based on helium-3 cooling system? So,
sure, I want to take a step at that if you don't mind hanging out for a minute or two. Yeah, feel free.
Yeah, so answer is simple. I mean, so this Large Hadron Collider doesn't use helium-3, so we use only helium-4, which is abundant.
Okay. If you have one more minute, Dr. Riley or anybody, here's one from Caleb. Caleb's contacted us through LinkedIn about this one. If there is, do you see a use case for data centers on the moon with or without helium-3? But do you see a use case for quantum computing data centers on the moon?
It's an interesting question. Not obviously so, in that obviously the challenge of building that. There's the power source for that. There are options there that are pretty interesting. The cooling is the other side of it with limited atmosphere. Again, radiative cooling needs to take a fair amount of that heat. That in principle is possible. Obviously, you can tile out a fairly large area. Probably the largest bottleneck there is the bandwidth of your communications systems as well. So all of that data between that data center on the moon has to, presumably if the use of that data is on Earth, then yeah, you need a fairly large bandwidth uplink to be able to enable that as well. So yeah, no, not impossible. It's not obvious to me right now what the use case of doing that would be, as opposed to other more remote places on the Earth. But yeah, open-minded as to how that may evolve.
And with that, I think we're going to conclude. So again, thank you, everybody, and we'll see you in May to talk about the legal aspects of mining helium-3. Thank you.
Thank you.
Yep, thank you.